So there was so far we've looked at two of the empirical gas laws, Boyle's law, Charles' law. And what I'm going to do is sort of skip over combined and Avogadro's and sort of put all these together into one gas law. And it's actually based on something known as the ideal gas law. And we're going to spend quite a bit of time on this. But I wanted to show you how you would use a law that looked like this, like you use Boyle's, right? P1 V1 equals P2 V2, or Charles V1 T1 equals V2 T2. How you can sort of bypass knowing what the law is if you just stick with this relationship that's down here. And I know it looks a little bit complicated, but I'm going to write it out for you so it, I think, makes a little bit more sense. So here's our first problem, and this is how I'm going to tell you to set these problems up. We're going to take and make a table again. So our table, if you remember, I have 1 and 2 on the left-hand side. And I'm going to read through the problem, and it says a piston containing 50 milliliters of oxygen at 15.1 kilopascals expands to 30.51 milliliters while being cooled from 95.3 degrees Celsius to 0 degrees Celsius. What is the final gas pressure? Okay, so there's a lot of information in here. So this is why it's important that you organize it. And what I typically tell students to do is just write the variables in this order. I'm going to put moles in here even though we don't need it. And then I put temperature at the end. And temperature, of course, will be in Kelvin, right? Everything else, it doesn't matter what the units are that you use as long as they're the same. So let's see if we can identify our P1, right? P1, let's say, is this. And what goes along with this is 15 mils of oxygen. And it expands to this volume. So that's V. This is V1 and this is V2. And it's cooled from, so this is T1. So this is P1 and this is T1. And this is T2. So now what we're going to do is write all the information out, and then I'll show you what the equation looks like, okay? Because it's actually sitting there right in front of you. You just don't recognize it the way it's written right now. So I have 15 mils, so I'm going to put 15.05 here. I'm going to put milliliters at the bottom because that's my unit. It's at 15.1 kPa, so I'm going to put 15.1 here, and the units are kPa. Oops, sorry. And then it expands to 30.51, so I'm going to put 30.51 here. And then, and it's being cooled from 95.3 degrees Celsius, so I'm going to just add 273.15 to it. And to 0 degrees, so that's just 273.15 Kelvin. So I don't need to add the 0 to it. I'm just going to write it in Kelvin temperature. But now what I need to do is I need to start calculating some values. So my T1 is going to be 368.15. And then notice that there's nothing said about the mole, so I'm going to cross that out. I won't need it. And I'm looking for P2. You'll notice that, and it is actually saying what is the final gas pressure. So again, one of the nice things about sorting your problems out like this, just like any equation, you're given enough information to solve for one variable. That'll be the one blank one, right? Now, what we need to do is write the equation, and I just wanted to show you this. The reason I set the table up like this is because it's actually the equation. Here's my pressure, here's my volume, here's my moles, and here's my temperature, and 1 and 2. And this is P1, V1, N1, T1. This is P2, V2, N2, and T2 like this. Right? Those are the references for the cells the way that the equation actually is written. That is the combined gas law. And what I mean by that, if you don't see it, I'm going to erase all and that, and I'm going to go like this. That's the equation that we're working with, and we're trying to solve for P2. Now, having said that, typically this is a difficult equation to solve, so for some students, the number of moles was not mentioned, so we assume that it doesn't change. And then I'm going to cross multiply to get everything out of the denominator. So I have P1 V1 times T2 is equal to P2 V2 times T1. And I just need to get P2 by itself. So I'm just going to divide by V2 and T1. And honestly, I really like when I do these problems to have my variable stack, is what I call that, so that when I write them, they're right on top of each other. It helps me stay a little organized, okay? So I'm going to divide through by V2 and T2, or T1, and those will cancel out like that. And so there's my equation, and what I can do now is I can just start plugging things in, and we'll use the table to keep ourselves organized. So I have P2 is equal to, now P1 is 15.1 kPa. And V1 is 15.05 milliliters. And then T2, so now we have to put 273.15, like this in Kelvin, sorry. And then on the bottom I'll have V2. So V2 is 30.5. That's in mLs. This is why I write the unit down here. They just all have to be in the same units, and so I make sure I try to enforce that as I go along. And this is going to be T1, which is 368.15 Kelvin. And then all these units will cancel, so my answer will come out in kilopascals. So I get 5.528, and the units are kilopascals, kPa. I have 3 sig figs in all this mess, so I'll round it to here, and it becomes 5.53 kPa. So it's actually at a lower pressure than it started with. It started off at 15.1. So let's see if we can look at this and see if it makes sense that it would be lower, right? So I went from a smaller volume to a larger volume, so that would, right, lower the pressure because they're inversely proportional. And then I went from a higher temperature to a lower temperature, and that would also lower the pressure because the temperature and the pressure should be directly proportional to each other. And so what you find is that the overall effect is a much lower pressure than when you started. Okay, here's another problem. It says a bacterial culture isolated from sewage produced 41.3 milliliters of dry methane at 31 degrees Celsius and 753 millimeters of mercury. What is the volume at STP? And now what you have to remember about STP is that standard temperature and pressure, and for this class, that's 1 atmosphere. Oops, sorry. 1 atmosphere. And 273.15 Kelvin. So this is what I want you to do is go ahead and follow the last example, right? Set up a table like I showed here, like this. Plug in the values and figure out what you're solving for. Then rearrange the equation, right? And then start taking the numbers from the table and sticking them into the variables for the equation, and then solve for your answer. Okay, so go ahead and get started. If you pause it, I'm just going to have the answer up when you're done, and we'll talk through it. Okay, just as a sort of checking point, I just filled the table out and looked everything up and converted everything. I just took the 41.3 as my V1, my initial volume, and my temperature that goes with that is 31 degrees Celsius, so I just automatically convert to Kelvin like this, and I'll fill that out when I actually solve it. But the pressure is 753 millimeters of mercury, and then for STP I put in 760 because 1 atmosphere is equal to 760 millimeters of mercury. And again, for my temperature, standard temperature is 0, so I wrote that in there. Normally, I would just write 273.15, but it's actually added to 0 in this case because standard temperature is 273.15 or 0 degrees Celsius. So now what you need to do is set up your equation, solve it for V2, and plug it in. Okay, so here's the solution to that problem. I went ahead and rearranged this equation, and like I said, I like to keep the variables stacked if I can because it's a good check for units as you're going along. So I have V2 is equal to P1 V1 times T2 over P2 times T1. I just leave a space here, but I know to multiply down here. So 753 is P1, and then 760 is P2. Now, it looks like 2 sig figs, but remember, this is part of the definition of STP, so it's an exact number. This is 41.3 milliliters for V1, and then T2, right, in the equation, it's T2 is 273.15, and then the bottom is 304.15. I actually had it sort of written out down here. You do the calculation, you get 36.749, and then you round it to 0.3 sig figs, so it's 36.7 milliliters. So there's a lot of problems, gas law problems, that can be solved this way. But what we'll look at next is another type of gas law, which was first developed empirically from all the combining of all the empirical gas laws, but it's actually known as the ideal gas law. So I say it was started as an empirical law, but since sort of development of better theory, we know that it derives from sort of physics, and physics ideas can be derived from sort of first principles, that is, like understanding like kinetic energy and temperature and all that kind of stuff. So this is the ideal gas law, and that's going to be used for most of the types of problems that you'll see for the remainder of this chapter.